K-mean clustering is an unsupervised machine learning algorithm. Today, we will discuss its principle of operation using Python. We'll uncover the hidden categories within a dataset and explain how to determine their optimal number. Finally, we'll go through its implementation step by step. Let's begin. K-means is a machine learning algorithm that divides a dataset into K categories based on the similarity of data samples to a typical or average representative of each category. Determining the value of K is a prerequisite of algorithm's operation, which is why it's part of its name. Let's explore step by step how the optimal solution is achieved. Let's assume we have a dataset described by two features. We can visualize this as a point on two-dimensional plane, which x and y coordinates correspond to the first and second feature. What we can observe with our eyes are three emerging groups, when the members of each group share more similarities with other members of the same group than with members of other groups. The question is how our algorithm can detect these similarities among group members and determine how many groups there should be. Well, first we need to make some assumptions. Let's start by assuming that the number of groups K we want to divide this data into is 3. This assumption can initially be based on domain knowledge about the problem and the nature of the data itself. Alternatively, we can begin with this value as a starting point and later compare the result with the different values of K. To proceed, we randomly initialize 3 points, where each point represents one of the categories we aim to identify. Let's start by considering a single data point. We will measure the distance between this point and each of previously initialized centroids. Next, we assign the data point to the category whose centroid is closest. We repeat the same operation for the next data point, assigning it to the category corresponding to the closest centroid. It may happen, and it's even expected, that some points will be assigned to the wrong category, as seen in this example. This occurs because the initial centroids were placed randomly. This process of assigning categories is repeated for every data point in the dataset, resulting in 3 groups of points in our case, 1 for each category. For each group, we calculate a new centroid by averaging the positions of all elements in that group. This concludes one iteration of the fitting process and shifts the centroids closer to their correct positions. In the next cycle, the entire process repeats, further shifting the centroids towards their optimal positions. This continues until all data points remain in the same group during consecutive iterations. In other words, the centroids' positions have reached the optimal solution. Once the model is fitted, categorizing new data becomes as simple as finding the nearest centroid and assigning its category. But what happens if the solution gets stuck in local minimum and the data grouping is not ideal? This can indeed occur, as the initial position of our cluster centroids were chosen randomly. The process of fitting the centroids can yield different outcomes, even on the same dataset. In 2 cases presented, the only difference lies in the choice of initial centroid positions. The solution is to run clustering process multiple times, each time initializing the centroids randomly and then selecting the best fit. In such situations, we face the question, what does the best fit mean? One way to answer this is to select the model for which the sum of squared distances between the data points and their respective clustered centroids is the smallest. This metric is called Between Cluster Sum of Squares, WSS. We can calculate it for each cluster and then sum the results. The model with the smallest total WSS is considered the best. Even for a simple dataset with clearly separable clusters, the algorithm can often stuck in suboptimal solutions. In this example, 2 out of 10 runs ended this way, as shown by the significant higher WSS bar on the chart. In our two-dimensional example, it's visually apparent that we are looking for a division of the data into 3 categories. However, in general cases, choosing the value of k is not so straightforward. So, how should we determine it? This is where within cluster sum of squares comes to our aid. We can fit the algorithm for each consecutive value of k, starting from 1 and ending on chosen maximum value, and plot WSS against k. We should see something similar to what is displayed here. It's important to note that for k equal to 1, no meaningful division occurs. In the extreme case where k equals to number of data samples, each point becomes its own category and WSS equals 0. What we are looking for is the characteristic elbow point on the chart, beyond which the reduction in WSS becomes less significant. You can think of it as a largest value of k that still results in substantial improvement in clustering quality, or in other words, a significant increase in intra-cluster similarity. Due to the shape of this chart, the method is applied called elbow method. The optimal value of k is found at the point resembling an elbow. Let's move on to the code editor, Visual Studio Code. The essential comes first, importing the necessary tools. These include the widely used library NumPy for operating on multi-dimensional arrays and the random module, as we will need to initialize certain values randomly. Now that we have essential in place, let's move on to a crucial element for this example, our data. We need to generate it randomly at the beginning, and for this purpose we will create a generateData function. We will also set a random seed at the start to ensure reproducibility of the random numbers. Next, we will create the 3 clusters of points on a 2-dimensional plane. For each cluster, we define its center using log parameter and its standard deviation using scale parameter. The shape of the returned array is specified in size argument, where we expect 50 data samples with 2 features each. Next, we combine all the points into a single array vertically using the VStack method, resulting in 150 points in 2-dimensional space. Now we will shuffle the rows of the array containing our data. This is commonly done in machine learning algorithms to prevent the specific order of the data from influencing the training process. Finally, the function returns the data. Now, let's move on to building the k-means class, which will represent our model. We start by defining the parameters. K, the number of clusters or groups into which the algorithm will divide the data. Each data will be assigned to one of the k clusters. Max iters, the maximum number of iterations during which the model will adjust the position of the centroids. This acts as a safeguard in case the algorithm does not converge to an optimal solution before reaching this limit. We set its default value to 100. Centroids, a list of centroids that will hold the coordinates of the cluster centers. This position will change during the training, and the final centroid location represents the model's learned knowledge about structure of the data. For the algorithm to function correctly, we need to implement a few additional methods. One of these will divide the data into k clusters based on the distances of each sample to the centroid of those clusters. To achieve this, we will prepare createClusters method and break the clustering process into steps. The first step involves reshaping the data and centroids arrays using the syntax provided by the NumPy library. By including the value none, we add an additional dimension in both arrays. This enables us to calculate the positional differences between each data point and every one of the k centroids. After this operation, we will obtain an array with dimension number of samples by number of centroids by number of features. We can think of the differences as a set of vectors for which we can compute their length, representing the distances between the points and the centroids they are compared to. To calculate these distances, we use the norm method from the linealg module. The norm function computes the vector norms along the last axis, which represents the coordinates of the vectors in the space. This operation reduces the last dimension of the array, replacing the series of coordinates with the single numeric value that represent the vector length. In the next step, we reduce another dimension of the array using the argmin function. This method returns the index of the smallest distance for each point, effectively replacing the series of distances with a single index. As a result, we obtain an array of indices where each index represents the closest centroid for the corresponding data point. Finally, we divide these indices into a subsets using a list comprehension. Each subset contains the indices of points assigned to a specific cluster. This is achieved with the where method, which filters and retrieves indices along axis 0 where the cluster matches the current cluster. The next key method is predict, which will classify data into one of the key categories. The return value will be the index of the appropriate cluster for each data sample. Essentially, it performs the same operation as the create clusters method in its first three steps, which we just discussed. However, this time, we condense the operation into a single line for brevity. When classifying data, we need a way to evaluate how good the classification is. To achieve this, we will write the method calculate WSS, which calculates within clusters sum of squares based on the provided argument data and clusters. This metric serves as an indicator of how scattered the data points are around their cluster centers. To accomplish this, we will create the list of WSS values for each cluster and iterate over all clusters, initially assuming that the WSS value is 0. If the cluster is not empty, we retrieve the coordinates of its points and sum the squared distances to their corresponding centroid. Since we are storing squared distances instead of distances themselves, we can sum the squared distances of coordinates using the sum method. In the next step, we append the calculated value to the WSS list and finally return the list at the end of the method. At this point, we can focus on what might be called the main method, the fit method, which contains entire logic for training the model. We'll start with the declaration that accepts one parameter where we will pass the training data. Right away, we will create a list to store the history of the entire training process. This will allow us to trace model progress later on. In the first step, we will initialize the position of the k centroids. We'll do this in somewhat random way. Instead of selecting completely random points, we'll place them at the position of randomly chosen data samples. For this, we'll use the sample function from the random module. This is not only strategy for initializing cluster centroids, but I expect that this approach will allow the model to converge to the center of point groups faster than if we used completely random points. With the starting point established, we can begin the process of fitting the data. This will be done in cycles, so we'll set up a loop. The loop cannot run indefinitely, so we need to define maximum number of iterations. However, we expect the algorithm to find optimal position of the centroids, which should cause it to terminate earlier. At the start of each iteration, we'll divide the data points into clusters based on the current position of the centroids. To accomplish this, we will use the create clusters method that we prepared earlier. For the current division of the data into clusters, we can calculate the within cluster sum of squares, WSS, using the calculate WSS method. Additionally, we can make prediction for each data point based on the current centroids. All these values, along with the position of centroids, will be stored in a dictionary. This dictionary will then be added to the history list, allowing us to track changes throughout the training process. Based on the previously assigned clusters, we will calculate the new coordinates of the centroids. This is done by averaging the position of the points within each cluster using the min method. If during any iteration the position of the centroids remain unchanged, it indicates that we have reached the local optimum. In such a case, we will break the loop before reaching the maximum number of iterations. Otherwise, we proceed to the next iteration, updating the centroid field with the new positions. After a certain number of iterations, the model fitting process will conclude. This may happen either because the iteration limit is reached, or, more desirable, because an optimal solution is achieved. In any case, this marks the ending of the model training. We finalize the method with a return statement that provides the accumulated history from all iterations. At this stage, we can say that our model is essentially complete, at least in terms of its basic functionality. However, there are two challenges we still need to address. One of them is the possibility that the model might fail to reach the best solution during training, instead getting stuck in a suboptimal solution that is far from ideal. To tackle this problem, we will prepare a multiple run function that trains the model multiple times on the same dataset using different random initialization each time. In the end, we will select the best possible solution, which minimizes the WSS value. Let's declare our function, which will take the training dataset data and the number of training attempts and runs as its parameters. At the beginning, we will create history list to store key metrics for each training run. Additionally, we'll initialize two variables, both set to none, to hold the centroid coordinates and the WSS value for the most optimal training attempt. Now, let's dive into the core of this method, the loop, which will execute as many times as specified in the nRuns parameter. During each iteration, we will reset the model centroids to none and train the model by invoking the fit method. At this point, we utilize the training history, run history. For each iteration, we append a dictionary of parameters describing the training process to the history list. These parameters include the centroid positions, the total WSS value, and the entire run history object, just in case we need to analyze it later. The key values for us at this stage are total WSS, as we will compare it in an if condition with the best result of previous training attempts, centroids, because we also want to preserve this as the final and most optimal solution. At the end of the method, we assign the best centroids to the appropriate field in the model and return the history of the entire process. To summarize, the multiple run method repeatedly trains the model, locks its parameter for later review, and finally select the best solution as the definitive result for fitting the K cluster to the input data. At this point, we are left with one significant challenge related to k-means algorithm. The code we've written so far assumes that we know the number of clusters k. However, in practice, the value of k is often unknown, so we need to wait to determine it. To address this, we'll use the previously mentioned elbow method. We'll create a new function, findOptimalK, which, similar to the multiple run method, will perform multiple iterations of fitting the data. This time, however, each iteration will use different value of k, incrementing it from 1 up to the maximum value specified by the max_k argument. At the start of the method, we will save the current values of the method's parameters k and centroids. This ensures that we can restore them at the end, since this is a method of specific instance of the k-means class, and the process of determining k will override these fields. Alternatively, we could create a standalone function or a static method and instantiate a new k-mean object for each trial. For now, though, we'll stick with this approach. As usual, we'll initialize a history list to store information about performance of the model during each trial. Once again, the core of this method is a loop that runs from k equal 1 up to max k. Inside the loop, we set the current value of k for the model, reset the centroids to none, and train the model using the fit method on the provided data. This time, within the history list, we store the two most critical parameters for each iteration: k, the number of clusters used for the fitting, and total WSS, which measure the quality of the clustering. This allows us to analyze the performance for each tested value of k. Finally, we restore the model's original parameters stored in the variables stored k and stored centroids. We return the fitting history, which is critical for further analysis. Using this history, we can plot the relation between WSS and k, helping us to identify so-called elbow point that suggests the optimal number of clusters. With our model class now fully implemented, we are ready to test its functionality in practice. The human mind often processes visual information more efficiently than long sequence of raw data. For this reason, I have prepared a set of utilities function in a separate file to help visualize the results. I won't go into the details of this helper function here, as they focus on drawing plots using Matplotlib library rather than explaining the core algorithm. However, you can find all necessary code and files on my GitHub repository. The link is in the description of this video. This function contains typical Matplotlib code tailored to match the data format used in our model. Here's a quick rundown of what each function does. Plot clusters display the data points assigned to their respective clusters along with their centroids. Plot optimal k visualize the history from the findOptimalK method, make it easier to identify the elbow point. Plot fit history show a series of plots for each training iteration, illustrating how the data and cluster divisions evolve. Plot multiple run history displays the WSS values for each training attempt conducted by the multiple run method. Let's begin with the imports. We'll use our k-means model along with the helper function from the plotutils file. Right away, we'll call generateData function to create the dataset we'll be working with. This gives us a set of synthetic data points that will serve as an input for training and testing our model. To demonstrate how our code works, we will perform 4 steps. We will create an instance of our model, setting the value of k to 3. We know our dataset and understand that this is optimal value. We will train our model using fit method. We will make prediction using predict method, which will return the cluster number for each data point. Finally, we will visualize the result graphically using the helper function plot clusters, passing in the data points, their labels, and the coordinates of the centroids. With the training history of our model, we can present its state for each iteration of training process. In our simple case, the model reached its optimum within a few steps. For comparison, we can train a new model using the multiple run method instead of fit. This approach provides a significantly better and more precise clustering of the data. The history object returned by multiple run has a slightly different structure and contains distinct data. By using the plot multiple run history function, we can access the training attempt history and observe how many of the runs result in high WSS values versus low ones. Finally, we can attempt to determine the appropriate value for k using findOptimalK. By plotting the data returned by this method with help of the function plotOptimalK, we observe a clear band at the value of 3. This is our elbow point, the value we have been using so far. And that's it for today on the k-means clustering algorithm. For now, thank you for your attention and I wish you a lot of fun with experimenting. See you in the next video.